Question 181. You have a Compute Engine managed instance group that adds and removes Compute Engine instances from the group in response to the load on your application. The instances have a shutdown script that removes REDIS database entries associated with the instance. You see that many database entries have not been removed, and you suspect that the shutdown script is the problem. You need to ensure that the commands in the shutdown script are run reliably every time an instance is shut down. You create a cloud function to remove the database entries. What should you do next? A. Modify the shutdown script to wait for 30 seconds before triggering the cloud function. B. Do not use the cloud function. Modify the shutdown script to restart if it has not completed in 30 seconds. C. Set up a cloud monitoring sync that triggers the cloud function after an instance removal log message arrives in cloud logging. D. Modify the shutdown script to wait for 30 seconds and then publish a message to a pub sub queue. The best approach is option D. Modify the shutdown script to wait for 30 seconds and then publish a message to a pub sub queue. Explanation. This option provides a reliable way to ensure that the database entries are removed after an instance shutdown by decoupling the task of removing the entries from the shutdown process. Here's why it works. 1. Pub sub queue. Publishing a message to a pub sub queue allows for asynchronous handling of the task. Once the message is published, it can trigger a cloud function that performs the task of removing the database entries, ensuring that the process is executed reliably. 2. Graceful handling. The 30-second wait in the shutdown script ensures that any in-progress operations on the instance are allowed to finish before the shutdown occurs. By using pub sub, the actual task of removing the database entries is handled independently of the shutdown process, reducing the risk of incomplete execution during instance termination. 3. Reliability. This method provides a robust mechanism for triggering the removal of entries even if the instance shutdown itself doesn't fully complete or if there are issues with the shutdown script. The cloud function will only trigger after receiving the pub sub message and can be retried if necessary. Why other options are less suitable? 1. Option A. Waiting for 30 seconds before triggering the cloud function can still result in a situation where the instance shuts down before the task completes. While it may work in some cases, it introduces unnecessary complexity and reliance on timing, which is less reliable than decoupling the task through pub sub. 2. Option B. Restarting the shutdown script if it has not completed in 30 seconds does not resolve the core issue of reliability. The shutdown process may still be aborted before the task completes, and there's a risk that the database entries won't be cleaned up as intended. 3. Option C. Using a cloud monitoring sync to trigger the cloud function based on an instance removal log message is less direct and more complex. Monitoring syncs are typically used for log-based alerts, not for reliably triggering actions tied to specific events like instance shutdowns. Pub sub is a more appropriate mechanism for triggering actions in this case. Conclusion. Option D is the best approach as it ensures that the database entries are removed reliably through a decoupled process. By publishing a message to a pub sub queue and having a cloud function handle the cleanup task, the process is made more resilient and less dependent on the timing or completion of the instance shutdown. Question 182. You are managing several projects on Google Cloud and need to interact on a daily basis with BigQuery, Bigtable, and Kubernetes Engine using the gcloud CL tool. You are traveling a lot and work on different workstations during the week. You want to avoid having to manage the gcloud CLI manually. What should you do? A. Use Google Cloud Shell in the Google Cloud Console to interact with Google Cloud. B. Create a Compute Engine instance and install gcloud on the instance. Connect this instance via SSH to always use the same gcloud installation when interacting with Google Cloud. C. Install gcloud on all of your workstations. Run the command gcloud components auto-update on each workstation. D. Use a package manager to install gcloud on your workstations instead of installing it manually. The best approach is option A. Use Google Cloud Shell in the Google Cloud Console to interact with Google Cloud. Explanation. Google Cloud Shell provides a consistent, cloud-based development environment accessible from any workstation with a browser. Here's why it is the best option. 1. Consistency across workstations. Cloud Shell runs in a managed environment hosted by Google, so you don't need to install or configure the gcloud CLI on your local machines. This ensures you always have access to the same environment, no matter where you log in. 2. Always up to date. Cloud Shell includes the latest version of the gcloud CLI, along with other Google Cloud tools, so you don't have to worry about updates or compatibility. 3. Ease of access. You can access Cloud Shell directly from the Google Cloud Console, making it simple to use wherever you are without additional setup. 4. Pre-configured tools. Cloud Shell comes pre-installed with tools like Kubernetes, Bigtable, BigQuery, BQ, and Bigtable commands, so you can seamlessly interact with your projects. 5. Portability. Since it's browser-based, you can use it from any device without installing or configuring software locally. Why other options are less suitable? 1. Option B. While creating a compute engine instance for gcloud usage ensures a consistent setup, it adds unnecessary cost and complexity. You would need to maintain the instance and connect via SSH each time, which is less convenient than using Cloud Shell. 2. Option C. Installing and updating gcloud on all workstations is labor-intensive and prone to inconsistencies. This approach is unsuitable if you are frequently switching between multiple machines. 3. Option D. Using a package manager simplifies the installation process, but it still requires manual setup and updates on each workstation. This doesn't solve the issue of managing gcloud across multiple machines efficiently. Conclusion. Option A, using Google Cloud Shell, is the most practical and Google-recommended solution for your use case. It eliminates the need for manual management of the gcloud CLI while providing a reliable, up-to-date, and portable environment for interacting with Google Cloud services. Question 183. Your company recently acquired a company that has infrastructure in Google Cloud. Each company has its own Google Cloud organization. Each company is using a shared virtual private cloud, VPC, to provide network connectivity for its applications. Some of the subnets used by both companies overlap. In order for both businesses to integrate, the applications need to have private network connectivity. These applications are not on overlapping subnets. You want to provide connectivity with minimal re-engineering. What should you do? A. Set up VPC peering and peer each shared VPC together. B. Migrate the projects from the acquired company into your company's Google Cloud organization. Relaunch the instances in your company's shared VPC. C. Set up a cloud VPN gateway in each shared VPC and peer cloud VPNs. D. Configure SSH port forwarding on each application to provide connectivity between applications in the different shared VPCs. The best approach is option C. Set up a cloud VPN gateway in each shared VPC and peer the cloud VPNs. Explanation. Cloud VPN provides a secure and reliable way to establish private connectivity between two networks, even when the subnets overlap. This approach minimizes re-engineering and adheres to Google-recommended practices for such scenarios. Here's why this is the best solution. 1. Handles overlapping subnets. Cloud VPN ensures secure private network connectivity at the IP layer without requiring subnet reconfiguration. Applications that are not on overlapping subnets can communicate seamlessly. 2. Minimal re-engineering. This solution does not require significant changes to the existing infrastructure, such as relaunching instances or migrating projects. 3. Security. Cloud VPN provides encrypted tunnels, ensuring secure communication between the two organizations. 4. Simplicity. Setting up cloud VPNs between shared VPCs is straightforward and doesn't disrupt existing configurations. Why other options are less suitable? 1. Option A. VPC peering is not recommended when there are overlapping subnets, as VPC peering doesn't support overlapping IP ranges. This would result in conflicts and routing issues. 2. Option B. Migrating projects and relaunching instances in a new shared VPC is disruptive, time-consuming, and labor-intensive. It would require significant downtime and effort to reconfigure resources, which is unnecessary for this use case. 3. Option D. SSH port forwarding is a manual and ad hoc approach that is neither scalable nor suitable for enterprise-level connectivity between applications. It lacks robustness, performance, and security compared to Cloud VPN. Conclusion. Option C, using Cloud VPN gateways to peer the shared VPCs, is the most efficient and Google-recommended solution. It provides secure, reliable private connectivity with minimal re-engineering while addressing the issue of overlapping subnets effectively. Question 184. You are managing several internal applications that are deployed on Compute Engine. Business users inform you that an application has become very slow over the past few days. You want to find the underlying cause in order to solve the problem. What should you do first? A. Inspect the logs and metrics from the instances in Cloud Logging and Cloud Monitoring. B. Change the Compute Engine instances behind the application to a machine type with more CPU and memory. C. Restore a backup of the application database from a time before the application became slow. D. Deploy the applications on a managed instance group with autoscaling enabled. Add a load balancer in front of the managed instance group, and have the users connect to the IP of the load balancer. The best approach is option A, inspect the logs and metrics from the instances in Cloud Logging and Cloud Monitoring. Explanation. Before making any changes to the infrastructure or application, it is essential to identify the root cause of the performance issue. Analyzing logs and metrics provides the necessary insights to diagnose the problem effectively. 1. Root cause analysis. Logs and metrics from Cloud Logging and Cloud Monitoring can reveal whether the issue is related to resource contention, CPU, memory, disk I/O, network latency, or application-specific errors. 2. Data-driven decisions. Observing trends in resource utilization, error rates, or request latency helps determine if scaling resources, fixing a configuration, or addressing a specific application issue is needed. 3. Minimized risk. Blindly changing instance types, restoring backups, or modifying deployment architectures without understanding the issue can lead to unnecessary costs, additional downtime, or loss of critical data. Why other options are less suitable? 1. Option B. Changing the instance type without diagnosing the problem is premature. The issue may not be related to resource constraints and could be due to a database bottleneck, application bugs, or external factors. 2. Option C. Restoring a backup of the database might lead to data loss if newer data exists. This approach also assumes the database is the problem without verifying it first. 3. Option D. Re-architecting the deployment with managed instance groups and a load balancer is a significant change that introduces additional complexity and cost. It may not address the root cause, especially if the slowdown is unrelated to scaling. Conclusion. Option A, inspecting logs and metrics in Cloud Logging and Cloud Monitoring, is the best first step. It allows for a thorough understanding of the problem before taking corrective actions, ensuring that the solution is targeted, effective, and minimizes potential risks. Question 185. Your company has an application running as a deployment in a Google Kubernetes Engine (GKE) cluster. When releasing new versions of the application via a rolling deployment, the team has been causing outages. The root cause of the outages is misconfigurations with parameters that are only used in production. You want to put preventive measures for this in the platform to prevent outages. What should you do? A. Configure liveness and readiness probes in the pod specification. B. Configure health checks on the managed instance group. C. Create a scheduled task to check whether the application is available. D. Configure an uptime alert in Cloud Monitoring. The best approach is option A. Configure liveness and readiness probes in the pod specification. Explanation. Liveness and readiness probes are built-in mechanisms in Kubernetes that ensure the health and stability of application pods during and after deployment. These probes directly address the issue of misconfigurations and prevent outages caused by releasing new versions with incorrect parameters. One liveness probe detects if the application inside a pod has become unresponsive or unhealthy. If the liveness probe fails, Kubernetes restarts the affected container, ensuring it can recover automatically from failures. 2. Readiness probe determines if the application is ready to handle traffic. Kubernetes only adds pods to the service endpoints if the readiness probe passes, preventing traffic from being sent to misconfigured or unready pods during a rolling deployment. 3. Prevention of outages. By using readiness probes, misconfigured pods are excluded from the load balancer until they are properly configured and healthy, ensuring that only functional pods handle traffic. Why other options are less suitable? 1. Option B. Health checks on the managed instance group apply to compute engine instances, not directly to GK. They are not relevant for Kubernetes pods. 2. Option C. Creating a scheduled task to check application availability adds complexity, is reactive rather than proactive, and does not integrate seamlessly with Kubernetes. 3. Option D. Uptime alerts in cloud monitoring notify the team after an issue occurs. While useful for monitoring, they do not prevent misconfigured pods from causing outages during deployment. Conclusion. Option A. Configuring liveness and readiness probes in the pod specification is the most effective way to prevent outages caused by misconfigurations during rolling deployments. These probes ensure that only healthy and properly configured pods serve traffic, directly addressing the root cause of the issue. Question 186. Your company uses Google Kubernetes Engine, GKE, as a platform for all workloads. Your company has a single large GKE cluster that contains batch, stateful, and stateless workloads. The GKE cluster is configured with a single node pool with 200 nodes. Your company needs to reduce the cost of this cluster but does not want to compromise availability. What should you do? A. Create a second GKE cluster for the batch workloads only. Allocate the 200 original nodes across both clusters. B. Configure CPU and memory limits on the namespaces in the cluster. Configure all pods to have a CPU and memory limits. C. Configure a horizontal pod autoscaler for all stateless workloads and for all compatible stateful workloads. Configure the cluster to use node auto-scaling. D. Change the node pool to use preemptible VMs. The best approach is option C. Configure a horizontal pod autoscaler for all stateless workloads and for all compatible stateful workloads, and configure the cluster to use node autoscaling. Explanation. This approach optimizes resource utilization and reduces costs without compromising availability by dynamically adjusting the number of pods and nodes based on actual workload demand. 1. Horizontal pod autoscaling, HPA. Automatically adjusts the number of replicas for a workload based on metrics such as CPU and memory usage. Ensures efficient scaling of stateless and compatible stateful workloads to match demand, avoiding over-provisioning or under-provisioning. 2. Cluster autoscaler. Automatically adjusts the number of nodes in the cluster based on the resource requests of pods. Adds nodes when demand increases and removes nodes when they are no longer needed, minimizing idle resources and costs. 3. Reduced costs. By combining HPA and cluster autoscaler, the cluster can handle varying workloads efficiently while maintaining availability, significantly reducing operational costs. Why other options are less suitable? 1. Option A. Creating a second cluster for batch workloads increases management overhead and may not significantly reduce costs since you would still need sufficient nodes for both clusters. 2. Option B. Setting CPU and memory limits improves resource allocation but does not address cost optimization directly. It does not dynamically adjust resources based on workload demand. 3. Option D. Changing the node pool to use preemptible VMs can reduce costs but risks interruptions for workloads, which could compromise availability. Batch workloads might tolerate preemptible VMs, but stateful and stateless workloads typically require higher reliability. Conclusion. Option C is the most cost-effective and scalable solution, allowing for dynamic resource allocation and optimal utilization of the existing infrastructure without compromising availability. Horizontal pod autoscaler and cluster autoscaler work together to reduce costs while maintaining the high availability of workloads. Question 187. Your company has a Google Cloud project that uses BigQuery for data warehousing on a pay-per-use basis. You want to monitor queries in real time to discover the most costly queries and which users spend the most. What should you do? A1. In the BigQuery dataset that contains all the tables to be queried, add a label for each user that can launch a query. 2. Open the billing page of the project. 3. Select reports. 4. Select BigQuery as the product and filter by the user you want to check. B1. Create a cloud logging sink to export BigQuery data access logs to BigQuery. 2. Perform a BigQuery query on the generated table to extract the information you need. C1. Create a cloud logging sink to export BigQuery data access logs to cloud storage. 2. Develop a data flow pipeline to compute the cost of queries split by users. D1. Activate billing export into BigQuery. 2. Perform a BigQuery query on the billing table to extract the information you need. The best approach is option B. Create a cloud logging sink to export BigQuery data access logs to BigQuery and perform a BigQuery query on the generated table to extract the information you need. Explanation. 1. BigQuery data access logs. BigQuery logs query details, including user information, query text, execution time, and data read. These logs provide granular insights into query costs and user activity. 2. Cloud logging sink. Exporting logs to BigQuery allows for structured storage and querying of log data in real time. You can write SQL queries to analyze query costs and user activity efficiently. 3. Real-time monitoring. Since the logs include information about ongoing queries, this method provides near real-time visibility into costly queries and user activity. 4. Scalability. Using BigQuery to analyze logs ensures that the solution can handle large-scale log data without additional operational complexity. Why other options are less suitable? 1. Option A. Adding labels to datasets and filtering via the billing page does not provide real-time insights or detailed query-specific information. This method is more static and limited to user-level billing details rather than individual query costs. 2. Option C. Exporting logs to cloud storage and processing them with data flow adds unnecessary complexity. BigQuery is better suited for querying structured log data directly, making this approach less efficient. 3. Option D. Activating billing export to BigQuery provides aggregated billing data, which does not include detailed information about individual queries or users. It is insufficient for real-time query monitoring and lacks granularity. Conclusion. Option B is the most effective and efficient solution, enabling real-time monitoring of BigQuery queries and user activity with detailed insights into query costs. By leveraging BigQuery for both logging and analysis, you ensure a scalable and straightforward implementation. Question 188. Your company and one of its partners each have a Google Cloud project in separate organizations. Your company's project, PRJ, runs in Virtual Private Cloud, VPCA. The partner's project, PRJB, runs in VPCB. There are 2 instances running on VPCA and 1 instance running on VPCB. Subnets defined in both VPCs are not overlapping. You need to ensure that all instances communicate with each other via internal IPs, minimizing latency and maximizing throughput. What should you do? A. Set up a network peering between VPCA and VPCB. B. Set up a VPN between VPCA and VPCB using Cloud VPN. C. Configure IAP TCP forwarding on the instance in VPCB, and then launch the following gcloud command from one of the instances in VPCA: gcloud gcloud compute start IAP tunnel instance underscore name underscore in underscore VPC underscore 822 backslash localhost port is equal to localhost 22. D1. Create an additional instance in VPC A2. Create an additional instance in VPC B3. Install OpenVPN in newly created instances. 4. Configure a VPN tunnel between VPC A and VPC B with the help of OpenVPN. The best approach is option A, set up a network peering between VPC A and VPC B. Explanation. Network peering. Google Cloud VPC network peering provides private connectivity between two VPC networks across organizations or within the same organization. It enables direct internal IP communication between instances in VPC A and VPC B with low latency and high throughput, as the traffic remains within Google's private backbone network. It is a simple and cost-effective solution for enabling communication between non-overlapping subnets in different VPCs, minimizing latency and maximizing throughput. VPC peering does not require additional gateways, tunnels, or encryption overhead, making it optimal for performance. Ease of configuration. Setting up VPC peering is straightforward. Both parties need to agree and configure the peering relationship. Why other options are less suitable? Option B. Cloud VPN introduces encryption overhead and additional latency, which is unnecessary since the subnets are non-overlapping and can connect directly via VPC peering. VPNs are generally used when encryption or connecting over the internet is a requirement. Option C. IAP TCP forwarding is designed for secure SSH or RDP access to instances behind firewalls, not for enabling direct communication between instances in different VPCs. It is unsuitable for continuous internal IP communication between multiple instances. Option D. Setting up OpenVPN adds unnecessary complexity, including managing additional instances, configuring the VPN manually, and dealing with encryption overhead. It is less efficient than using Google Cloud's built-in network peering feature. Conclusion. Option A is the best choice as it ensures low latency, high-throughput internal IP communication between instances in VPC A and VPC B with minimal configuration and no additional infrastructure overhead. Question 189. You want to store critical business information in cloud storage buckets. The information is regularly changed, but previous versions need to be referenced on a regular basis. You want to ensure that there is a record of all changes to any information in these buckets. You want to ensure that accidental edits or deletions can be easily rolled back. Which feature should you enable? A. Bucket lock. B. Object versioning. C. Object change notification. D. Object lifecycle management. The best approach is option B, object versioning. Explanation. Object versioning. Object versioning in cloud storage keeps a record of all versions of an object when changes are made or deletions occur. When you enable object versioning for a bucket, cloud storage retains all previous versions of objects in the bucket. This allows you to reference or restore previous versions as needed. It ensures you can recover from accidental edits or deletions, making it an ideal solution for maintaining a history of changes and ensuring data integrity. Use case fit. Since the information in the bucket changes regularly and past versions need to be referenced, object versioning meets the requirement by maintaining a historical record of all changes. Why other options are less suitable? Option A, bucket lock. Bucket lock is used to enforce retention policies, ensuring that objects cannot be deleted or modified until the specified retention period has elapsed. It does not maintain previous versions of objects. While it is helpful for compliance and regulatory purposes, it does not address the need for versioning and rollback. Option C, object change notification. Object change notification sends notifications about changes to objects in a bucket but does not maintain a record of previous versions or allow rollbacks. It is used for triggering downstream processes when objects change, not for version control. Option D, object lifecycle management. Object Lifecycle Management automates actions like transitioning objects to a different storage class or deleting old versions of objects based on predefined rules. While it helps manage storage costs, it does not inherently store or allow reference to previous versions of objects. Conclusion. Option B, Object Versioning, is the correct choice because it provides a record of all changes, enables rollback, and allows access to previous versions of objects, addressing the need for data recovery and version history. Question 190. You have a compute engine application that you want to autoscale when total memory usage exceeds 80%. You have installed the cloud monitoring agent and configured the autoscaling policy as follows. Metric identifier, agent.googleapis.com/memory/%_used. Filter, metric.label.st8 is equal to used. Target utilization level, 80. Target type, gauge. You observe that the application does not scale under high load. You want to resolve this. What should you do? A. Change the target type to delta_per_minute. B. Change the metric identifier to agent.googleapis.com/memory/bytes_used. C. Change the filter to metric.label.st8 is equal to used and metric.label.st8 is equal to buffered and metric.label.st8 is equal to cached and metric.label.st8 is equal to slab. D. Change the filter to metric.label.st8 is equal to free and the target utilization to 20. Option C is the correct answer. Explanation. 1. Understanding memory usage in cloud monitoring metrics. The metric agent.googleapis.com/memory/%_used tracks only the memory classified as used. However, in Linux systems, memory usage includes buffered, cached, and slab memory, which might still be available for applications but is not considered free. To accurately reflect actual memory pressure, the filter should include these additional states: used, buffered, cached, and slab. 2. Why the original configuration does not work. The current filter is only tracking metric.label.st8 is equal to used, which might not represent the actual pressure on memory. Since Linux reclaims cached memory when needed, an instance may appear to have low, used, memory while still having high total memory allocation. 3. Why option C works. By adding buffered, cached, and slab, the autoscaler will make decisions based on total memory pressure rather than just the used category. This ensures the instance scales correctly when the system is under memory stress. Analysis of other options. Option A, delta_per_minute incorrect because memory usage is not a rate-based metric. Gauge is the correct target type. Option B, bytes_used instead of %_used incorrect because the issue is not with the metric identifier but with the filtering criteria. Option D, metric.label.st8 is equal to free and target utilization to 20% incorrect because scaling based on free memory is not a best practice. The system could still have available memory from caches even if free memory is low. Conclusion. The correct fix is option C, which ensures the filter accounts for all relevant memory states, used, buffered, cached, and slab, so that autoscaling triggers correctly when memory pressure is high.